It's doing it. Okay. Hi, everyone.
Hi.
Okay. Okay, so this is a joint work with Merav Parter and Moni Nao. Just before I begin, I want to say, please be rude, okay? If you have a question, just immediately ask me. You don't have to raise your hand. I have like 100 slides, and I can talk about this for like 3 hours. So Daniel, you have to stop me at some point. And I don't want to cover everything, just I want you to understand something. So please ask questions. And especially if I speak in some language that is for academics and say things that I think are well defined and they're not. Okay, so I want to talk about interactive proofs, and I want to talk about distributed algorithms, and I want to combine them together. And this is why this is a joint work with Merav Parter, which is an expert about distributed algorithm and fault-tolerant designs and stuff like that. And Moni Nao, which is famous for many things, but maybe in this context, he's along with Cynthia Dworf, the inventor of what we know today as proof of work, and non-malleable cryptography, and a lot of other cool stuff. Okay. So interactive proofs. This was a notion that was defined by Goldwasser, Mikhail, and Rakov. Okay, the three of them up here. Actually, I think it's not 89. I think it's before 85. Yeah, this is one of these papers that took a long time to get accepted. And maybe because they introduced this cool notion of interactive proofs and the notion of zero knowledge within the same paper, which really is too much to get. And they had no applications in the original paper. And people were like, okay, why is this interesting? Okay, so what is an interactive proof? Okay, so this is going to be our user, okay, the verifier, and this is going to be our all-powerful prover. And the goal of the prover is to convince the verifier of the truthful of some statement, okay? He's saying, oh, this statement X, this is a correct statement. And they want to run a protocol, a dialogue, and the prover is trying to convince the verifier. And just for an example, okay, of something that is hard to prove, you have this graph, and the claim is that this graph is not 3-colorable, okay? I cannot color the nodes of this graph such that the coloring is legal. A legal coloring is that if I'm colored with red, then all my neighbors are colored with a different color, okay? That's a valid coloring. How can I prove that the graph is 3-coloring? Okay, if it was 3-coloring, I would just send you the coloring, okay? And then verifying is very easy. You just go over all nodes and you check the neighbors. That's very easy. But how can I prove that the graph is not 3-colorable? Okay? Except of course, the brute force approach of going over all possible colors. Okay. So again, more academic, okay? We have some instance X, and to prove the truthful of some statement, we define something that denoted by L. We call this a language, okay? For example, the language can contain all graphs that are not colorable in 3 colors, okay? And then I'm asking, is X in this language of graphs that are not colored with 3 colors? Okay, what are the requirements from such an interactive proof system? We want first what we call completeness, is that if the statement is true, okay, meaning X is in the language, so it's a truthful statement, then the verifier is going to accept at the end of the dialogue, okay, with high probability. So accept with some tiny probability, it's going to say, okay, yeah, you know what, you convinced me, the graph is not 3-colorable, it's okay. If we didn't have this, then the protocol wouldn't be useful. What is the security of the protocol? Okay, we call it soundness. If X is not in the language, if it's a false statement, then we're going to require, again with high probability, that the verifier at the end is going to say, no, I don't accept, this proof seems wrong. Okay. Exactly in the middle, okay. So This notion of interactive proof, except of being super cool and exciting, really led to some very important notions. So it led to the notion of PCP, okay, probabilistic checkable proofs. This is a method to encode proofs in a way that you can verify them with just reading like a constant number of bits from the proof. Okay, and used today, I guess, even you guys use them today in your companies. And it led also to zero-knowledge proofs, okay? So a zero-knowledge proof was really maybe the motivation for interactive proofs. Interactive proofs are very, very powerful. So by a theorem by Adi Shamir, based on previous work, IP equals P-space. So IP is the class of all languages that have interactive protocols, IP. And we ask, what can we prove with IP? So of course, we can prove things like NP, okay? Like, yeah, the graph has a 3-coloring. You just send the proof, and that's it. But it's actually much more powerful. It equals to P-space. So this is really saying that any algorithm that has some reasonable size memory, okay? So there's P-space, there's polynomial size memory, okay? So for example, this exponential algorithm that went over all possible colorings of the graph and checked them one by one. It was an exponential algorithm, but it had very small memory, just needed to enumerate over the colorings. So this is the reason why we have such an efficient interactive protocol for this problem. Okay? So you can just transform any exponential algorithm with small space to an efficient interactive protocol. The prover in this particular example won't be efficient, of course, okay? But the verifier will be very efficient. Okay. Still focusing on interactive proofs. When should we use an interactive proof? Okay? And this is an important question. When should you use an interactive proof? Maybe the most classical setting would be, okay, I have a verifier. This verifier is weak. Okay, maybe it's my laptop or my cell phone. I have a prover. This prover is very powerful. Maybe it's some cloud or something like that. And he wants to convince the cell phone of the truthful of some statement, and you don't trust the cloud, so you want a proof. Other examples of course, if zero knowledge, okay, if the prover is more powerful because he knows something and he doesn't want to reveal this secret. But actually, you can use interactive proofs in any setting where the verifier is somehow limited, okay? And this limitation doesn't apply to the prover. So it could be the case that the verifier has small memory, okay? And the prover has a lot of memory. Maybe they have the same running time, just different in memory. Maybe the verifier, cannot do plus, it can only do minus, okay? That's also okay. In this talk, I want to talk about interactive proofs where the verifier is a distributed system, okay? So here I'm looking at the distributed system as a disadvantage, okay? Because the verifier, instead of being one machine that has the whole input and can run some arbitrary algorithm, now the verifier is actually going to be a distributed system. So it's going to be many, many nodes. The input is going to be spread out among these n nodes. And now the whole system needs to somehow coordinate and say if they accept the proof or not. Yeah, I said be rude.
Yeah, sorry. So I want to take one step backward. You said that this interactive proof system is compatible or suitable for more cases where the verifier may be weaker than the prover. So yeah, so what I want to ask is, like, can you give an example for some proof system where this interactive proof system is maybe superior in such cases? Because I'm missing the comparison against a different system.
I'm not sure I understood your
question.
question.
You said that this interactive proof system
Yeah.
is suitable when the verifier is weaker than the prover.
Yeah, in any setting that the verifier is in any way weaker than the prover.
Yeah, so my question is there another proof system, like non-interactive, where this interactive proof system is superior, given that the verifier has less resources? Oh, it's understandable. If not, then we can take it off.
No, I didn't understand.
Okay.
I'm saying it could be that the verifier has limited memory, it could be that the verifier has limited amount of randomness, or in this example, the verifier is a distributed system. We'll see. But I think that wasn't your question. Yeah, so, okay.
Like maybe just as a follow-up, and I don't know if this is what you were trying to say or not, but it triggered something. Like today, for example, thinking about some snarks, right? So succinctness is kind of this property that the proof is short and constant, and the verification time is very short as well. So in this case, this is also optimal for situations where the verifier is weak, right?
Yeah,
I mean,
the verifier is...
But it's not an interactive proving system.
It has a few properties, right? First of all, zero knowledge.
Yeah.
Okay, so that's one way of the verifier being weak. He doesn't know some information.
Oh, I see. So
Second of all, you also want the verifier to be like super efficient, where you want the prover to have a bit more computation power.
Okay, so I get two things from your answer. One is that weakness is not only computationally, and
yeah, it's not only computationally.
And two, that when you say that an interactive proof, then you also mean like kind of the non-interactive version of that interactive proof system? Is that like...
Yeah, we're going to talk about in general interactive proofs, and I'm going to also talk about how you can compress them, do Fiat-Shamir like you do in snags, and make them non-interactive. Okay, but the snags are actually interactive things where you assume a random oracle and compress them to be non-interactive, right? So actually the way we get these good snags is by thinking of many rounds, okay, proving our protocol, and then just collapsing it. Okay, and this is going to be relevant here also. Okay, so some motivation. Why would I want to think of such interactive proofs? So this is a good question. These are examples that we thought of, but you can give me more examples. Okay, so think of a first example of a computer network. And I don't know, I'm an IT and I have my network, okay, and IT of Google, I have a lot of computers. And I want to verify that the network is like too connected, okay? There's no like single fault. If something falls, there's another way to bypass this router or something. So there's standard algorithms to check this, okay? And I can check this in the network, but then I want to check it like every month, okay, or every day, or every year, I don't know. And I'll need to run this algorithm again and again and again. And instead I'm saying, okay, run it once, maybe work a bit harder, and don't only check that the network is okay, but have a proof, okay? Create a proof that the network is okay. And then verifying this proof is very efficient. Okay, so this is one place where we'll have a network that would want to verify some proof. Okay, in this example, it wasn't interactive. Another example is like a Bitcoin or a blockchain network. Suppose you have some company that has a coin or something, and they claim that, okay, our network is such and such, and all the transactions were, legal and apply all the fees that they should pay and everything. I don't know, they have some general claim on the network, and the user wants to verify this claim. So the network tells this company, okay, prove to us. I cannot check this claim on the whole network. It's very big. There was many transactions. Give me a proof that what you're saying is correct. Okay, and this is also can be an interactive proof. Maybe last example, think of some data scientist that worked very hard to analyze a lot of data and get to his results. And he publishes these results in a paper, and it's accepted to Nature. And then people want to read this paper, see the results, and verify it. Okay, how do I know that the scientist actually did the right computation and got to the results? So you can tell the scientist, okay, work a bit harder, create a proof. Okay, and it's going to be a non-interactive proof, okay, after we collapse it. And then anybody that reads this paper can very efficiently just check this proof. Okay, and here the network is like the cluster of computers that is running on. Okay, we'll see some more concrete examples shortly. Okay, let's comment on the motivations. Recently, this was actually used in some follow-up work. They were using it to check safety properties of the implementations of distributed systems. So you have like some implementation, and then there's the specifications of this algorithm. Then you want to check at every step that you're actually following the specifications. And they used it actually to implement a consensus algorithm.
So blockchain was the first application.
Well, yeah. Okay. So distributed NP. Okay, so before I want to talk about distributed interactive proofs, let's talk about the non-interactive version, okay? The NP version, the analog to NP. So this was introduced by Corman et al. They called it proof labeling schemes. So we have some network, okay? So every node in this graph is a computation unit. And there's some graph that defines the communication pattern, okay? Which computer is connected to which computer, and they can send messages. I'm going to assume that the graph is connected throughout the talk. Okay, and now I have this prover. The prover wants to prove something about the graph. Okay, so how does he talk to the nodes? So we're going to connect him directly. Okay, so the prover is connected directly to each node in the network. Okay, you can send a proof to every node in the network. So every node U in this network. So initially they have, I'm going to assume they have some ID, okay, like their IP or I don't know, Bitcoin address or something. This is not numbers between 1 and n. These are just unique IDs. And they also, let's just assume they know the ideas of their neighbors. Okay, that's like how they talk to them. The prover is going to send this message mu. Okay, this is like the proof. And this is just a notation that this is a string of length L. Okay, some parameter L. So it's going to send a different, so this is mu. So this is a different proof, okay, for every node U. And he's going to send it to the nodes. The nodes are going to exchange these proofs with their neighbors. Okay, so if I'm a node, I'm going to send this proof to my neighbors. Okay, not to the entire graphs, only to my local neighbors. And after that, after this single step, we need to decide if to accept or reject. Okay, and L is the parameter, is the proof size. Okay, I'm going to say that if all proofs are of length m, I'm going to say that the protocol has a proof size of length L. So what are the requirements? They are as follows. So what is the statement? Okay, what is the input here? It's going to be the graph. Okay. So for example, if I want to prove that the graph is not three-colorable, so my instance is actually the graph. Okay. It might have also additional inputs, as we're going to see. Okay. For example, if I have the graph and it's already colored, and I just want to check that this is a valid coloring, so my input is the graph and the colors. So every node has also additional input. So my instance is the graph and possibly additional inputs to every node. And I want completeness. If X is in the language, if our statement is correct, then all nodes are going to say, yes, I accept. The security or the soundness, if X is not in the language, the statement is incorrect. I want that there will be at least one node that will say, raise a flag and say, hey, this is a not correct statement. Okay, I'm not requiring that all the nodes do this. This is actually impossible. We require that at least one node. Okay, and then later he can maybe propagate this information. Okay, let's see an example. Okay, if you're puzzled by this precise definition, the most obvious example is three coloring of a graph. Okay, it has a very nice distributed NP proof. Okay, the NP proof would be just the coloring, and just notice how it's naturally distributed. The prover will just send each node in the network its color in a valid coloring, and then they just exchange this color with their neighbors and verify that this coloring is valid. Okay, so the proof size for proving a graph three-colorable is going to be constant. Okay, 2 bits. Okay, I need 2 bits to describe 3 colors. Okay, 1.5 bit. Okay. When you define a new model, you want to check the triviality of this model. Okay, so let's see what is trivial. A prover can send the whole graph, so that's n squared bits, plus the whole set of inputs, just send it to all the nodes. Okay, this is a huge proof. Okay, this is like everything, all the information. Okay, just to see the extreme case. And then what do the nodes do? They're gonna check that everybody got the same proof, so he's not lying, he's not sending like different graphs to different people. And they're gonna do the local checks. So they're gonna see that their local view of the network is consistent with the whole graph that the prover sent. And then once they have all the information, okay, I'm not restricting the running time of the nodes. Okay, this is really more talk about the communication between the nodes, okay, and the number of rounds. So once they have all the information, then you can just solve the problem locally and know if X is in the language or not. Okay, so this is like the trivial regime of the problems. So we would like protocols that have much less than n squared bits, okay, of proof size. Okay, let's see an example. A spanning tree. Okay, we have a graph, we want to compute a spanning tree. This is maybe the first step in many algorithms. And there's a very easy algorithm to compute a spanning tree, but it can take many rounds. Okay, there's a distributed algorithm, you can compute a BFS tree of the graph. But this would take the diameter of the graph rounds. Okay, what happens if we add a prover? Can he help us to compute a tree quicker? Okay, the prover knows everything. Okay, the prover knows the graph, he knows everything. Okay, but we don't trust him. So what is the prover going to do? He's going to send every node U just the ID of its parent in the tree. He's going to compute some tree and send the ID of its parent of the tree. Okay, this is great, but this is not enough because we don't trust the prover. So we ask him to additionally send du. Du is going to be the distance from the root. Okay, so distance 0, distance 1, distance 2, and so on. Okay, so he's also going to send the distance from the root, and also the ID of the root. Okay, so everybody knows who the root is. What is the verifier going to do? Okay, so every node in this graph is going to check that the distance that he sees from the root is the distance of his parent plus 1. Okay? So he verifies if he got 3, then his parent must be 2, and so on. Okay? No, this is 2, this is 1. Yeah. And do I have a... Okay, yeah. And why is this important? Because the fact that we know our parent in the tree is not enough. The prover could, for instance, give us a cycle. Okay? It could not be a tree, it could be a cycle. But if he gave us a cycle, then there's no way that he gave the distance to the roots that are consistent among the cycle. Okay? So this check will fail for some node. Okay, if you have a cycle, then this node has value 2, then he's going to check that his parent has value 1, his parent has value 0, and then his parent cannot have value -1. Okay? And the proof size in this case is log n bits. Okay, because you just need to give an idea of a node in the network. There's n nodes, so this log n bits. Let's see another example of why I need this tree. Okay, this tree allows me to compute a linear function of values all over the network. Okay, so let's suppose, so this is a xv. Okay, let's suppose that every node in the network has some value. Okay, just some value that he has. And my goal in this example is to compute the sum of all these values of the nodes. So this is a global function. Just go over all nodes and compute the sum of all the values. Again, I can do this in diameter of the graph rounds. Okay, start computing and propagating the information. But with the prover, I claim that I can do it with 1 round. Okay, I just need a proof from the prover, and then I can verify this with 1 round. So what is the prover going to send us? What is the proof? The proof is going to be this value SU, which is the sum of all the XV values, okay, but not for all nodes, for TU. What is TU? TU is the subtree rooted at U. Okay, so if this is the node U, TU is this subtree. Okay, and TR is the whole tree. Okay, every node has its own subtree. So I ask him to give me all these partial sums of all the subtrees. And then what does the verifier need to do? Okay, so this node has the subtree of everything here. So he's gonna get the subtrees of his children, add them up, add his own value, and just verify that this is consistent. If everybody check that this is consistent, then it's consistent on the leaves and on the second level and so on, up to the root. Okay, and the root has the value of everything. Okay, has the sum of all the values. Yeah, questions? Okay. So all the examples I showed up to here were non-interactive. Okay, the prover would send one message to the nodes. The nodes would exchange this proof with their neighbors and accept or reject. So that was distributed NP. Recently, Cole et al. Introduced an interactive version of this proof labeling schemes. Okay, so I'm gonna define here just like 2 rounds, okay, and this naturally generalizes to more rounds. So this is gonna be called distributed AM. This is Arthur-Marlin protocols, okay? Never mind. So we have every node, and he's gonna send a random string RU, so this is like the challenge of the verifier, okay? But here, the whole network is the verifier, and every node is gonna sample an independent challenge, RU. Okay, again, of L bits. So the proof length is L, so also the challenge is of length L. The prover is gonna respond now with a proof MU, okay, a proof for every node. And the nodes are gonna exchange this randomness, okay, the challenge and the proof, and decide to accept or reject. Okay, and again, I want the completeness that if X is in the language with high probability, all nodes accept. And if soundness, if X is not in the language, it's a false statement. With high probability, there exists a node that rejects. Okay, so this is the 2-message version. You can think of a 3-message, 4-message, and so on. Okay. Okay, so what are our results? So we give a very general compiler, a general method for translating standard interactive proofs, okay, interactive proofs that we know and studied for many years between a single verifier and a prover. And the method translates them to a distributed interactive proof. Okay, and the cost of this compiler is going to be proportional to the efficiency of the verifier in the standard proof. Okay, and I'm going to explain what I mean exactly. So if I started here with an R-round protocol, standard R-round protocol, and the verifier was very efficient, okay, he had some time-bound T, okay, so the running time of the verifier was some parameter T. Okay. Then I'm going to have a distributed, so this is DIP, this is distributed interactive protocol. The number of rounds is going to be R plus 2. Okay, so I paid 2 more rounds. And the proof size is going to be T over N times log N. Okay, so in particular, let's say the running time of the prover was N. Okay, so the proof size is going to be actually log N. So it's going to be a log N, a very short message to every node in the network. We have 2 more results and 2 more compilers. I'm not sure I'm going to talk about them very much. But if the running time was too large, but the space, okay, the memory used by the verifier was small, so we can also exploit this. And we have a compiler for small space verifiers. And similarly, if it had a lot of space, but the depth of the verifier, when you write it as a circuit, okay, if it's a shallow circuit and has small depth, then actually you can get also a very good distributed protocol. So this almost, I would say, like covers all protocols we know, okay? Unless really the verifier is like, has a lot of running time, a lot of space, and is very sequential, okay? So it doesn't have small depth. Okay, but in this case, we have like a compiler for each case. Here you pay more, you have a constant, some arbitrary constant, and here you have some polylog and factors. Yeah?
So I guess the paradigm is that you go from standard interactive proofs to distributed interactive proofs. You pay some price for the compilation, but then you can gain something. You can get either a time improvement, space improvement, or that.
What you gain is a verifier, okay, that can check the proof without knowing the whole input. Like this is a distributed system, so the input itself is not stored at any single computer. And this network with one round of interaction can say, yes, I agree this statement, this global statement on the entire graph and values that all the network has, I agree with it.
Sure.
This is the advantage.
A naive implementation of a distributed interactive proof is just send the proof to one node and have that node
Yeah.
decide, right?
Yeah, exactly. So you'll have the equivalent of that, but with the proof size, instead of being something that is proportional to the whole graph, it will be proportional to like log n. So logarithmic in the size of the graph.
And those
So instead of-
you either gain time, space, all that improvement. Not all of them together.
Like a combination, I don't know, you choose which is best. Like,
So those are different cases.
these are different cases, yeah. And actually the way you implement this is by applying this. And so it's really reduction. So I don't know if anybody knows, this is like based on what's called the GKR protocol, and this is based on the RRR protocol. So if anybody knows, so that's how we get them, but never mind.
So just another question before we continue. You said that this is a compiler for any interactive prover to become an distributed interactive proof for the verifier to become a distributed verifier. I have the question of does the compiler map any number of rounds prover to a one-round prover all the time, or is it like 1 to 1?
No, so this is how you pay in the number of rounds.
Oh, that's number of rounds. Sorry.
Yeah, so you started with an R-round protocol, you're gonna pay 2 extra rounds. But this is even a constant, it's like additional 2,
Yeah.
okay? And here you're gonna pay R plus some constant, and here is gonna be additive polylogan factor. Okay?
Sorry.
Yeah, no, you don't, I told you to be rude.
Okay, thanks. So will the verifiers need to trust the compilation?
Yeah, good question. So what do the verifiers do? So assuming you know the protocol of the first of the standard interactive proof, so every node would just like know its line in the new proof. So it doesn't need to trust or get this information. It's just something that you can take the code of the standard proof and compile it yourself, and this is what you want.
Like every node would compile.
Every node would take, yeah.
What's their place in the graph?
They don't know exactly where you don't know where you are in the graph.
Oh, you just know it's a determined. Yeah.
Okay, you have some unique ID
Yeah.
that you can distinguish between people, but I have no idea how the graph looks like.
Yeah, I mean the actions of the nodes are the same.
Yeah,
wherever
so
you
the
go.
compilation itself, like I don't need to know the graph to have the new code of what I need to run. Yeah. Good questions. Okay. Okay. Yeah.
So I'm understanding it correctly. So in order for the distributed verifiers to be secure, they must like trust each other. Like that when one
Yes. Yes.
one
A good
rejects
thing.
that,
So let me
it's
say,
propagated.
the verifier is a distributed. So I treat the whole verifier as one distributed system. Yes, if I have like some nodes in the network that collude with a cheating prover, then they can fool me. Okay? But you have to understand this is like how to define. It could be the case that the whole graph is colorable with 3 colors except one node. Okay? And then if I don't trust this node, then I just have no way in the world, okay, to see that it's not colorable. Okay, so this is, but yes, the whole network is here considered the verifier.
By the way, you said like sending one color traditional. I mean, it's totally unnecessary that the two topologies are similar, like the distributed network and the graph you want to prove on. Two different things.
Yes, so I have the network. I'm calling this the graph. And maybe there's an additional graph that they want to prove that is three-colorable. This would be part of their individual inputs. Okay, so I always have the graph. I call it the graph, the communication graph. And then they might have, like, in their private inputs, more graphs. Okay, but if they cannot communicate on this graph, then it's just considered in the private input part. Okay, and the statement that we're trying to prove to can depend only on the communication graph, and it can also depend only on the inputs and would not care about the communication graph. Okay, and these results hold for any graph. It doesn't matter. I don't need the graph to be an expander or something or have large connectivity. It just needs to be connected. Okay, and actually if the graph is not connected, there's really nothing you can do. Okay, as I said already, if you guys know how to compress rounds using a random oracle, this is called the Fiat-Shamir paradigm. So you need a bit more care here because it's a distributed system, so it's not so obvious how to apply the random oracle, because I cannot take a random oracle and apply it to my input, because my input is the graph and nobody knows the graph. But with a bit more work, you can actually make this work. And if I assume I have this random hash, random oracle, okay, in the sky, then you can take any distributed interactive proof and compile it to a non-interactive distributed proof, okay? So exactly like snugs, once you compress, it's not a proof anymore, it's what we call an argument, okay? It means that only a computationally bounded prover will not be able to convince me of a wrong statement. Okay, if he does only a limited amount of queries to the random oracle, then he won't be able to find a wrong proof. I saw some question.
I don't know if I want to ask this, but I guess not all interactive protocols are interactive just for the sake of generating random numbers, right? I mean, okay, sure, you can take a protocol that the interaction is for the verifier to generate numbers.
You're talking about like a public coin protocol where the, yeah, okay. So I'm going to talk about public coin protocols. Public coin protocol is what the verifier does is choose random strings and send them to the prover. And at the end, he takes all the information and runs some arbitrary computation to decide if to accept or reject the proof. There's the transformation from private coin protocols to public coin. So this is not, this is like without loss of generality up to like efficiency of the prover. But anyway, I'm going to focus on public coin protocols, and these are like the vast majority of protocols, I would say. Okay. So again, this transformation uses a random oracle. There are some results. I only put this to tell you there's some result on Lydia Election. I guess with the time being, we won't have time to see it. But Lydia Election is like some source of consensus, okay? 10 minutes, okay. Yeah. So I have 10 minutes, so I want to show you some proof, okay? And what we're going to see, okay, if you lost us by now, okay, so I'm going to define a new problem. It's called set equality, a very clean problem, and we're going to show, I think, a very nice protocol for it. And this is actually the heart of all our compilers, okay? This protocol for set equality. And this is actually what was used by this follow-up work, Panda, in their system. Okay, so what is set equality? Okay, so I have two sets and I want to check that they're equal. Okay, that's very, very simple. So what are these sets? So every node U is going to have two values. I'm going to have a value and a b value. So on my right hand, I hold some a value, and on my left hand, I hold some b value. Okay? And okay, these values are in some field, I don't care, these are numbers, okay? And I'm gonna define the set A. So the set A is just the set of all the A values, everything that sits on all the nodes in the graph on the right hand. And the set B is all the values that sit on the left hand, okay, all the B values. Okay, and my goal is to verify that A equals B as sets, okay? So I don't care about the order, there's no order of the nodes in the network, just that the values are the same values, the same set of values. And I actually care about multisets, so if a value appears 7 times in A, I want it to appear 7 times in B. Okay, but how can we check that A and B are the same? Okay, I have 7 here and 10 here, and maybe Daniel, which is far away from me in the graph, has the 10 and some 3, and somebody else has 3 and 5, and so on. Okay, so this is a bit hard to check. And we're going to use ideas that go back actually to Lipton, 89. I didn't find the previous reference. I think this is the first one. And this is a method to use what's called, okay, read Solomon codes. Okay, I'm going to explain everything. But the encoding is going to be in a way that is invariant to the order. Okay, because we want to check equality of sets and not of some specific strings. Okay. So we have this set A, and we're going to somehow encode it as a polynomial PA, okay? A polynomial of degree n, and this is just going to be the polynomial. So what is this polynomial? So what is the roots of this polynomial? Okay, so just by the way I wrote it, the solution to this polynomial, okay, x would be any AI, okay, any AU, okay? Because then it's a product of many things, and one is 0, so it's going to be a 0. Okay, so for example, this is the polynomial. If I had 3 elements here, then it would be x minus 4 and x minus 1/2, I don't know, and so on. Okay, and the product of these terms. And B is going to be the same, okay, just the product of all these terms. I noticed that indeed the order didn't matter, okay? It doesn't matter in what order you give me the A values, you get the same polynomial. Okay, great. I have 2 polynomials. And you need to prove this, but you can observe that these polynomials are the same polynomial if and only if the 2 sets are the same set as multisets. Okay? So what is a multiset? So if I had a value many times, this would be a root that occurs in the polynomial with a bigger multiplicity. Okay, so I have 2 polynomials. I want to check that they're the same polynomial. How do you check the 2 polynomials are the same polynomial?
They need to agree on the number of points as their degree.
Exactly. So either the 2 polynomials are the same, and if they are different, even slightly different, it doesn't matter. They can agree only on a small number of points. Okay? So think of 2 polynomials of degree 2, okay? If they're different, they can agree only on 2 points, okay? So if I just choose a random element, okay, I'm just going to choose a random element in my field, and now I just need to compute this polynomial on this single random element, okay? And if they differ, then I know that they're not the same polynomial. And if you want better soundness, then you just do parallel repetition. You do this many times, okay, to get better soundness. So we only need to compute this polynomial on a random point S. And this takes us back to the trees, okay? And the example of how to compute some function, some global function on the graph, okay? Because this is like, instead of summing up some value of the graph, this is like multiplying, okay, some value on the graph. I have this nice example of 2 polynomials, yeah. Okay, so this is the actual protocol. So the prover is going to send to the verifier a tree, okay, rooted at some node R. So he's not going to send only the tree. He's going to also send a proof that is actually a spanning tree, okay, but we talked about that already. The root of this tree is going to sample this field element S and send it to the prover, okay? And then the prover is going to send every node this capital AU value, okay, which is the same thing, okay? It's the product of all these terms on the subtree of U. Okay, so this is like evaluating this polynomial, but not completely, only with respect to your subtree. Okay, and the verification is the same. Everybody checks that the product of all their children times what they see, okay, is consistent. Everybody check consistency of this point S, that the prover didn't lie and say that they send different S to different nodes. And what we get is actually that you can check set equality in a DMAM. So this is a distributed IP protocol with 3 rounds. So this is Marlin, Arthur, Marlin. Okay, so this is 3 rounds. And the proof size is log n. Okay, so it's a very small proof. You can actually make this 2 rounds. Okay. So I don't have much time. Let's just see this and maybe one word about the compiler, and I think we'll be done. So let's just see the power of this set equality. And this is actually a problem that was posed as an open problem. So here, every node has a unique number. So usually in a network, every node has some ID, okay? Some, let's say, my IP, some unique ID. But now I want the prover to give the nodes unique numbers between 1 and n. How can I verify that the prover actually gave me numbers between 1 and n? Okay, and he, like in a permutation, he didn't give two nodes the same number. I can, of course, check that my number is between 1 and n, but I don't know that he didn't give 2 nodes the same number. So we have this set of n numbers, a1 to an. Every node has its own number, au. And we want to check that this is actually a permutation of the numbers 1 to n. Okay, this is a shorthand for all the numbers 1 to n. So the solution is actually a reduction to set equality. Okay, so how we're going to reduce this thing to set equality? So they already have the a values, okay, that they already had. They don't have b values. So we're going to define the b values to be au plus 1 mod n. Okay, and why does this work? I'm going to do proof by example. Okay, just one example, you see that it works, and you can believe me. So let's say these were the a values. So it's really a permutation of the numbers 1 to 4. So what are going to be the corresponding b values? So 3 plus 1 is 4, 1 plus 1 is 2, 4 plus 1 is 1, and so on. Okay? And you can see that this set is actually equal to this set. So the set equality is going to tell us yes, okay, accept this statement. What happens if he lied and he gave 1, 3, 2, 2? So look at the b values. They're going to be 2, okay, and then this is going to be 4, and then 3, 3. Okay, and these two are not the same set. Okay, so we're going to reject and cut him that he lied to us. Okay, and this holds in general. So we get that permutation has a distributed AM protocol with log n bits. Okay, previously it was known only with like n log n bits, something that is proportional to the size of the network. I have like 2 minutes? Yeah, okay. So let me just say how this is related to a general compiler. And our compiler takes the verifier, treats it as a RAM program, and compiles it. I'm going to show here a simpler version. Okay? So we're going to assume that the verifier can be implemented by some small circuit. Okay? And we're going to see this. So assume pi is some public coin protocol. Okay? Public coin as you ask. How do we compile this to a distributed protocol, pi prime? Okay, so first, we're going to ask the prover to send us IDs between 1 and n. Okay, and we're going to verify this ID. We just saw how to do that. Okay, so this is just one component that we already built. Then we're going to simulate the whole protocol by just distributing the messages from the prover and the verifier, okay, to all the nodes. What do I mean? If in the original protocol, the prover would have sent some message, some big message to the verifier, then he just cuts it up to blocks, okay, to even blocks. The first block is going to send to node number 1, the second one to node number 2, and so on. Okay, really just distribute the communication. Okay, remember this is a public coin protocol, so all the checking only happens at the end. Okay, the whole protocol is just exchanging information at the beginning. And the same with the verifier. If the verifier would choose some big random string and send it to the prover, so now every node is going to choose just a part of this random string. Okay? and send it to the prover. And because we have IDs, we know how to reconstruct this thing, okay? Because the ID number 1 will be the first part, and so on. Okay. Now, let V be the final computation of the verifier, okay? At the end, the verifier needs to check many things, okay? So he has the graph G, okay? G is the graph. R is the total amount of randomness that was sent throughout the protocol, and M is the whole proofs that was sent throughout the protocol, okay, in all the rounds. And somehow the verifier needs to run on all these things and see if the output is 1, is accept, okay? And we need to somehow magically compile this step, okay, to a distributed protocol. Okay, so now I'm going to assume that this algorithm V, okay, let's think of it as a circuit, okay? So what is a circuit? Okay, I have, these are the inputs, okay, like the input bits to the computation, and then you have gates, and they're connected, and this is the final output. So we're going to ask the prover, okay, so if I'm node number 1, we're going to number all the gates, okay, so all the gates are numbered, and if I'm node number 1, I'm in charge of the first gate. If I'm node number 2, I'm in charge of the second gate, and so on. If there's more than n gates, you just do modulo n. Okay, if there's 2 n gates, then every node is going to be in charge of 2 gates and so on. You just divide the gates between the nodes. And then I'm going to ask the prover to run this computation and give me the values on the wires. So if I'm node number 4 and I'm responsible to this gate, I'm going to ask him to give me the value here and the value here. Okay, if I'm this gate, I'm going to ask him to give me the value here, and the value here. Okay, just give me all the intermediate values of the computation. Okay. Now, what can I do locally? I can just check locally that, yes, the OR of this value and this value is actually this value. So I check locally that what he sent makes sense. What is the problem here? Okay, that this wire is the output of G4, and is also the input of G6. And G4 could be somebody on one side of the graph, and G6 could be somebody on the other side of the graph, okay? And I have no idea that if he told me that the value here is 7, that he told the other guy that the value is also 7. Okay, so he can send here inconsistent values, okay? And I cannot check this. So G6 is not a neighbor of G4 in the graph, not necessarily, okay? So what I do, I denote by W all the input wires. So notice that any wire here acts once as an input wire to this gate and once as an output wire for this gate. Okay, it has 2 hats. So by W denote all the input wires, and by W prime denote all the output wires. And then what is left to check? It's left to check that these 2 sets of values as sets are equal. Okay, that it didn't lie. So I'm gonna encode the name of the wire and then its value. Okay, and then I have the set of input wires and its values, the set of output wires and its values, and I need to verify that these 2 sets are equal, and we just run the set equality protocol. Okay, I think I'm gonna wrap up, right? I'm way out of time. So let me just move to the last slide. This is you can do something for RAM programs. And I told you I can talk for hours.
100 slides.
Yeah, okay. I'm just going to say, because this is a zero knowledge meetup, at the end, after you do everything distributed, there is a way to generically transform them to zero knowledge using standard zero knowledge protocols, okay? So I have my V on zero knowledge. Conclusions, we talked about distributed proofs where the verifier is distributed. One main observation that is adding rounds here adds a lot of more power to the verifier. And this is good because we don't care about more rounds because we can compress them at the end. Academically, maybe a big open problem is showing lower bounds. Lower bounds for interactive proofs are very hard to get. And in this distributed system, it's a bit easier to show lower bounds, so this could be a good step towards showing lower bounds for interactive proofs. You can change the model a bit. You can say what happens if the graph, if all the nodes share some private randomness, okay, some global shared randomness that is not known to the prover. Does this give more power to the prover? And lastly, of course, more applications, and I would like to see this more in use in other settings. Okay, thank you.
Any further questions?
Where's my water?
Maybe I have one short question. Is like, what's really the concrete efficiency of this kind of compiler? And is it something that if we implemented would give something like useful for some applications?
Yeah, that's a good question. Let me first say maybe a small comment that I didn't say, that the efficiency of the prover is pretty much preserved through this process. It's a bit hard for me to answer, because if you would ask me a few years ago, I would say that all of these things are completely out of reach of being practical. But now actually we have a lot of these protocols, and I know some companies that actually implement zero knowledge. And I would say that if the original protocol was practical and efficient, and you have like a good representation of your algorithm as circuits, okay, which is usually the case with these things, and I would say that this is practical.
So what's today like the most efficient interactive proving system? Is that?
I don't know, like depends on the setting. Either you focus on zero knowledge, and that's one thing, or maybe you do like this GKR protocol, which is like pretty efficient, where you prove statements about parallel statements. Okay, I don't know like exactly what are really practical.
I'll ask you, I'll bother you another time.
Yeah, but as you saw, like there's there's nothing like crazy theoretical happening here. Mm-hmm. Okay, like evaluating polynomials and all this stuff are morally the usual things that are done in these zero knowledge proofs anyway.
Any more questions? So let's thank our speaker once more.